In this video, we are going to talk about the hinge joint. Now, earlier on in our introduction video, we mentioned that joints are a way that you can constrain the behavior of your rigid bodies along some axis. And the hinge joint's job is to do exactly as the name suggests. It allows you a hinge that you can revolve around.
Right, think a door.
Yeah, a door is a really good example. I mean, if you have a door inside of a scene and got a doorknob for it, you expect this to swing inward or perhaps outward. And so to do that, you would create a hinge along the inside that it could spin around. So let's take a look at how we can set this up. So I'll jump into Unity. Now I need some sort of an object we can use. I'm going to keep things very simple here. We'll use basically just the geometry that's included. So let's start off with a cube. And I'm going to put it right in front of my car. And this car we actually created in an earlier video over the wheel collider. If you didn't see that, it was actually pretty cool. Now let's scale this down in Z. I'll make it kind of tall. I do not want it to penetrate into the ground, however. So I'll lift it a bit up into the air. Now let's say we wanted this to swing kind of like a doggy door. So let's turn this into a rigid body first. So component, physics, drop on a rigid body, and then we'll go back to component physics, and this time we'll drop on a hinge joint. Now, we are fortunate in that by default this is already kind of working like a doggy door. Here's the hinge joint component, and in just a moment I'll go over its various properties. But for now, let's just take a look at what we get when we first apply it, and it looks like my view kind of jumped a little bit. You see this little tiny orange axis on top? It actually gets smaller as I approach it, so I can't really get any closer than that. In fact, it might be easier to see if I back off a little bit. This tells you the axis around which you will be spinning. So without doing any further setup, just leaving things exactly how they are, if I hit play, my car rolls forward, and it bumps the door and pushes it up like so. Pretty cool. Now, that shows the behavior pretty well, but we can change a lot of things around with the hinge joint by adjusting its properties. So let's take a look at those. First off, we have the anchor for the hinge joint. This allows us to change the point of attachment for our hinge. So if I increase this in Y, you can see that we're now attached way up here. Now, what I'm going to do is crank this way up. So you see that orange axis is really high in the sky. Now let's hit play and watch really carefully how the door rotates when it's hit now. See, it's hit as if it's anchored really high up in the air now, as opposed to being right at the top of the door.
Right, it's more like a pendulum at that point.
That's right. Now conversely, we could pull it down a little bit inside the door, and now watch what happens. You see, we're spinning from a point that's actually inside the door itself. So that's what anchor does, really. It just allows you to position the point of the hinge itself. We'll set that to 0.5, which will get us right up to the top of the bounding box one more time. Now, moving down from here, we have the axis. This allows you to control the axis about which you want to spin. It's controlled as a vector, so if you want to get some really cool rotation, you can start playing with various combinations. But really, if you're just doing something simple like this, we would be rotating around the x-axis. So, I mean, we just leave that at 1. If we wanted this to rotate as if it was a door, like, say, to your house, we need to rotate around the y-axis. So I'll set x to 0 and set y to 1. And now I just need to produce the appropriate offsets. So let's take our anchor, and I'll slide it down in x until it's right on the edge of the door. And because we're rotating around the y-axis, the actual y-altitude of the anchor doesn't really make any difference. So now I am going to double check my positioning because I don't want to completely stop the car. So I'll slide it over, so we're just going to hit maybe right there on that one part of the wheel. Make sure I'm not penetrating into the ground at all, which it looks like I very well may be. So we'll pop that up a little bit because that can cause errors if you have that kind of penetration. Let's hit play and watch the door, and bump, it swings around.
And it gets caught on the terrain geometry on the other side.
Yep, it smacked into the terrain as if it was a door jamb. Now, let's put that back the way it was. I'll take my anchor, set it back to 0 in X. Let's take our axis, and we'll set that to One, you'll just notice here, since I've combined X and Y, we're starting to get an incident vector, which is pointing out like so. But we'll leave this back at X. We're still kind of revolving like a doggy door. Now, we have some really cool stuff that we can turn on and off and control. We have the ability to use spring, a motor, and limits. A spring allows us to cause this door to try to maintain a specific position and to almost kind of like bar doors. A really good example would be like doors in an Old West saloon.
Yeah, I was thinking like a screen door with a big spring.
There you go. Any kind of door that has a spring to try to pull it back to a given position. It's exactly how this works, but I keep going back to the bar doors. Now, here we have a little kind of a doggy door. It rotates upward, but we can still use this. So first off, if we want to use a spring, we need to turn it on. So we check Use Spring, step down inside the properties, and you have three very simple properties. You have spring, damper, and target position. Target position tries to, this is going to be the rotation that you'd like to try to achieve. So if I was to set this to, say, 90 degrees, like so. Now, if I just hit play, not much very interesting is going to happen. In fact, the door is just going to look like it's just sitting there, and nothing special took place. That's because while we've given this a target position, we haven't given it any strength, and that's where spring comes in. The spring property allows you to control how strong that spring is going to be. So as I increase this, let's say we push this up to 20. Now we hit play. You see the spring is automatically pulling it right up to 90 degrees, and it's trying to put it there. It doesn't immediately just jump right to it. It's fighting gravity. It's fighting the actual center of gravity as this door is pulled down by it, and it's resisting.
Right, it has some mass.
That's right. So we can go ahead and stop that. And I realize it's a little bit tricky to see when I have to rotate the camera around, so what I'm going to do is grab my first-person controller. I'm going to rotate him so that he's automatically facing what I want him to see, and I'll pull him back a little bit. And let's just hit play again. So now we can see that just rotate right up into the air, straight out of the gate, and it's stopping our little car there. Now let's move on down with the rest of our properties. Now let's say we don't really want to use the spring. Actually, let me talk about the spring damper. What this is going to do is apply a dampening effect. It's going to slow down the velocity of that spring. If you have, this is actually more important if you have a really powerful spring. If you've got something that's really, really forceful, you may want to apply some dampening to kind of soften up that effect a little bit. It's a resistance force to how much force is already being applied to the spring itself. So let's see, if I do something really crazy, like set this up to 500 and we hit play, we jump out really, really quick. But then as I take my damping, the damper, and crank this up to 50 is probably way over the top, but we'll just try it anyway. And I keep hitting 0, and I don't mean to, so sorry about that. There we go. And you see there was a little bit of resistance as it approached that value, and nowhere near as much springiness at the end.
Right, it looks more like a shock absorber more than an actual spring at that point.
That's true. Now, I'm going to double that, and you can see how it gets really slow there toward the end. And that's because that damper is resisting that motion. So it's like the spring and the damper are always going to be fighting each other. Now let's go ahead and turn off Use Spring, and let's jump down to Motor. Now, Motor is exactly what the name suggests. It allows you to take this joint, this hinge, and start forcing the object to spin around it, as if it had a motor attached to it. It has a target velocity, it has a force, and it has a free spin setting. Target velocity is the velocity that your object is going to try to approach. It's an angular velocity, how quickly the thing is going to rotate. Force allows you to control the maximum amount of force that will be used to achieve that target velocity. Think of it as a rate of acceleration. The more force you have, the quickly you're going to get up to your target velocity. So if we set this to, let's just throw some values in there. Let's just try 20, but we'll leave our force at 0, and we're not going to get anything particularly interesting yet again. And we'll take our force and set it to 5 just for starters. Still not much. We're going to have to really crank it up for that.
I got to check Use Motor.
Oh, yeah, make sure you're actually turning on the motor, Zach. You can totally make fun of me for that one if you like to, but at least somebody caught it. So there we go. With a value of 5, it's slowly pushing around. but it is reaching it. Now let's crank up the target velocity. Let's set this to 200, so 10 times the value it had before. Donk. And you can feel that force. You can feel that little bit of resistance as the car hit it at first, and then it didn't immediately just knock the car out of the way. So we miss, and then it thumps and pushes, and then it eventually shoves that car back out of the way, which is very, very cool. We can turn that force way down, and you can see what happens. We hit our velocity, but then it takes a lot longer to shove our car out of the way. And then conversely, we could go back up to our car, and if we take a look at its rigid body, its mass is currently set to 5. Well, let's set that to 50. And thunk, and it just can't fight it. It tries, but it just can't resist the mighty car. So let's take our mass on the car. I liked some of the results I was getting there, so let's just delete that, and we'll leave that at a mass of 5. So does the motor make sense so far?
Oh, yeah. Makes sense.
All right, so we've got our target velocity, we have our force, and then we have free spin. Now, this is a little bit difficult to show. What this means is that the motor can only accelerate the object. It can't slow it back down. So if some other force comes along, if we consider this this door, and it was maybe spinning in a counterclockwise direction already, at a fairly slow rate, and then something came along and just blasted it and caused it to spin even more quickly, by default, the motor's going to notice that and try to slow it back down to its target velocity. If you have free spin activated, it will only speed up. So if some other force comes along and knocks your object around so it's spinning even more quickly, that'll just happen until it slows down naturally based on drag or some other factor. Free spin means you're only accelerating. You're not decelerating at all. It's kind of like having a 10-speed bike or a ratchet, where you're pushing the pedals forward, but then you can roll them backward and they don't really do anything. It's the exact same thing. Now let's go ahead and turn off use motor. Let's jump down to use limits, which I'll go ahead and turn on first this time, so I don't get kind of embarrassed like last time. Now use limits is pretty straightforward. This allows you to establish a min and a max value of rotation for your hinge. So currently we could set this to a min of 0 and a max of 90. And let's just see what we get, because I'm not sure which direction I'm going to actually rotate in. And it just thumps. You can actually, if you look really close, I'm actually going to stop and hit play again. Currently we're hitting our min value. So technically we want our max to be negative 90. But if we take a look, you'll see there's a little bit of give there in that door. So just keep that kind of thing in mind. If you're expecting these physical simulations to be absolutely perfect and it's never going to rotate past that minimum value, don't count on that. The physics simulator is going to try to achieve these limits, but if a really strong or high mass force comes along, it's going to have to resist that. Now let's set our min to negative 90, and let's just see what happens.
Or max them. Negative 90.
I said, well, max to negative 90. And now it's allowed to rotate, and that looked great. In fact, because I moved the camera a little soon, I'm going to go ahead and just hit play one more time, so you'll see it's now allowing the car to push the door right out of the way. No problem. But what happens if we restrict this to, say, only 20 degrees? And just for the sake of it, because, earlier I moved that door kind of off to the side, I'm going to center it back up on the car. And let's see, 20 degrees is going to be enough for the car to get by? No, it's not. So at 20 degrees, it thumps, and that's the end of it. Now, let me go ahead and hit stop. We have min bounce and we have max bounce. This is how bouncy the hinge is going to be when you hit the min or if you hit the max. This controls how much motion energy is going to be re-imparted back into the object. So if we just really crank this up, let's take now we're hitting our max value. So let's just start with our max bounce. And we'll set this up to something really ridiculous. Actually,
1's a max.
It's a 0 to 1. Okay. I want to crank it. I want to crank everything to like crazy levels.
What it's doing is how much force it hits that backstop with is going to be sent back into the object.
That's right. And it didn't have that much force to begin with. So we're not really seeing much of a bounce. But if we had a really high velocity impact, it would hit an impact and it would bounce back with just as much force as the door actually used when it reached that position. So however much torque was used to rotate us back to 20 degrees, that same amount of torque would be reapplied in the opposite direction to send us back forward again. Now we'll go ahead and set that back off to 0, and this brings us down to brake force and brake torque. This is where we can get into breaking these joints, literally taking the objects that are constrained to this point in space and breaking them off. I'll give you just a little bit of a heads up. For simplicity's sake, I will only be demonstrating brake force and not brake torque. Brake torque works exactly the same way. You just need some other force that would come along and spin the object beyond whatever your torque level happens to be to cause the thing to break off. But because all I've got is the ability to roll this car into my objects, it's a lot easier for me to demonstrate with brake force. So let's take a look at this value. Currently this is set to infinity. If you type infinity into this value, your joint will never actually break. If we pull this down to something like 1 and let our little car roll into it, boom, it eventually got to a point where it broke it free and then our door just fell off. Now we can do all kinds of things. We can fine-tune that quite a bit, actually. If we set this up to something like, well, let's try tripling it. So we set it up to 3. Now this means that the car should, by default, have a really hard time breaking that hinge. And so you might have slow cars that pass through, and it's no problem at all. But what if a car came through that was just blastingly powerful? It was just screaming through, and how are we going to make that happen? Well, we could take the car itself, go up under component.
Uh-oh, rocket engine time.
It's time for a rocket engine. I think so. Let's go under physics, and we'll drop on a constant force. And we want this to work in the relative z-axis. Actually, we could go on world z as well, but it's not really going to matter that much. And let's put this... I always just want to try values out, so let's just try 50 first and see what we get. Bam! And that didn't break it at all.
Not enough force.
We need more power.
Oh, boy.
Blam! And that breaks it off, no problem. And then the car races up the tree and off into the sky. And I'm sorry if my overzealous shout startles you there, but that's just too great, really. And shoom! So obviously you can have a lot of fun with that. So that's a quick look at how you can break things. Now, on the hinge itself, there was a property that I skipped over, and that is connected body. And I skipped over it on purpose. To show it off, though, I'm going to take my brake force, and we'll set this back up to infinity, and let's take our rocket car, and let's turn its engine back down. So I'll just leave it at 0, but I'll leave the constant force there in case I need it again for any given reason. Now, what I'm going to do is take my door, and I'm going to duplicate it and move it up into the air. What connected body allows you to do is to attach a rigid body to another body in space.
Right. By default, these hinges or these joints are constrained to the world.
That's right. Which is why that little doggy door, this little door we've been working with, is just floating in space. We've literally constrained it, locked it in place relative to the world. However, we don't have to do that. In fact, I could take this guy and duplicate him up even higher, so I get 3 whole levels out of this. I just have to make sure that my connected bodies are associated properly. So let's do this. I'm going to take my 3 cubes. Let's make a brand new game object, which I'm going to call doors. Let's put all 3 of my cubes in there. And then we'll take the time to rename them just so there's no confusion. That'll actually be really important here in just a moment. Let's call this bottom door, middle door, and top door. Which works in reverse alphabetical order, which is fine. So we'll start off with the top door. The top door isn't going to be anchored to anything but the world, so we can leave its connected body property alone. Now, the middle door needs to be anchored to the top door. So what I'm going to do is, without releasing the mouse button, see, if I just click on top door, I switch up to top door. But if I have middle door selected and I click and drag from top door, I keep my focus on middle door and I can drag it over like so. So here's top door now set up as the connected body for middle door. I grab bottom door, then drag middle door onto his connected body, and I've just created a chain. The bottom door is connected to the middle door is connected to the top door. Now we hit play, take a look at what we get, and boom. And they're nicely connected together just like a chain. So that's it. That's really all there is to a hinge joint. You've got the ability to control the anchor, which is the point of attachment, the axis, which is the axis about which you'll be turning. You can use springs, motors, and limits to control the behavior, and you can apply an amount of brake energy that can be exerted either linearly or angularly to snap this object off of its joint. That, however, is going to wrap things up for this video. Thanks for watching.